Good morning. Well, it's morning here. I don't know when you're watching this, but it's morning right now. It's Friday. I wasn't really planning on doing this today, but I'm going to do it anyway. So I ate too much for breakfast, so I'm feeling a little bit, So I'm going to try and suck in the whole time. If I pass out, it's something to send into the America's Funniest Videos. All right, so here's the lesson. We got rational versus irrational numbers. Rational numbers, as it says, are numbers that can be written as fractions or as I gotta switch to pen apparently, or as decimals. Okay, certain type of decimals which we'll get into. So that is, they can be terminating decimals, meaning, you remember from before, that the decimal stops, it terminates. At some point it will terminate. And repeating decimals. Okay? And you remember from that lesson, hopefully, that we got terminating decimals and repeating decimals by converting fractions into decimals. Also, these square roots of perfect squares, that really is the same thing as any of these numbers. You can also take, like a regular 5 or 6 or something like that and change that to a fraction as well. So anything that can be written as a fraction is a rational number. In fact, the word rational numbers, the word rational, involves mainly that word ratio, which is a comparison of two numbers using division. So 2 over 5, 12 over 1, anything like that. So perfect squares, we only list that here because to differentiate it from the non-perfect squares. Okay? So irrational numbers, you cannot write them as a fraction. It is absolutely impossible. They are irrational, not rationals. I don't know what that IR means. I know in Spanish it means something, but that's not here. So irrational numbers include things like pi and, wait, what? No, that's wrong. It's kind of decimals. Irrational numbers include non-terminating, that's embarrassing, non-terminating and non-repeating decimals. Okay, they go on forever and they don't repeat. So these ones, either they will stop or they will repeat at some point. Okay, one of those two things. They will stop or they will repeat. These ones don't stop and they don't repeat. Okay, looks like a bunch of random numbers. Okay, these would also look like the square roots of non-perfect squares. Okay, and I closed my multiplication table, but again, the perfect squares were all the ones down the diagonal of the multiplication table, and all the other ones are non-perfect squares. So we'll look at what are some rational and irrational numbers here. So, rational or irrational. Okay, this first one here, negative 12, that is rational. And yes, you do need to write rational and not just R or I, because you're not going to remember what that means, and I don't care if you say you're going to remember what it means, just write rational anyway and irrational anyway. Okay, explanation, I can write that as a fraction. And we can just put negative 12 over 1. I could also do negative 24 over 2, whatever. Okay? Pi, if we look at pi as a decimal, it is that 3.141513589653323846275028819716939937, etc., 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 etc. Okay? I just have a poster on the back. I read it. So that is irrational. That is one of the very first irrational numbers that many people learn. Okay? Non-terminating non-repeating. Okay. 0.6. We look at that decimal. Does it go on forever? Sometimes it's easy to look at. Does it go on forever without repeating? It just stops. So it is a terminating decimal. That makes it rational. So you could write terminates. There's an I there. Okay. You could write that it terminates. You could also write that it's a fraction. You could change that fraction. We say that as 6/10. Okay? Or how do we say that? 6. That's the tenths place, so 6/10. 7/8, by definition of a rational number, that is a ratio. 7/8. So it is a fraction. 1, 2, 3, 4, 5, 6, ... And that's a decimal. Okay? Do we know what's coming next? Probably 7, 8, 9. It has a pattern. I don't know what comes after 9, if that's a 0 or a 1, 0 or a 1, and then 1, 1, 1, 2, 1, 3, 1, 4. I don't know. I have no idea. Okay? But it's not repeating. It's not ending. We're going to call that irrational. I'm not sure that you could find a value for that. But you can create it as an irrational number that doesn't have a thing. I don't know. Maybe you could. People smarter than me probably could. Non-terminating, non-repeating. I'm just going to cursor that ish. Let's write it fast. Okay, 0.33 with repeating bars. Well, that follows in the up there thing that's up at the page, at the top of the page, that it is a repeating decimal, so that makes it rational. Okay? It is repeating as a fraction. That is 1/3. Okay? Again, every rational number, every single one, 100% all the time, every single rational number can be written as a fraction. Irrational numbers cannot be written as a fraction. Okay, square root of 20, is that a perfect square? Well, I have, what? By there we have 9 and 16 and 25 and 36, so that is not a perfect square. So that is irrational. Okay? It is the square root of a non-perfect square. Forgot a second over there, sorry. Square root of non-perfect square. It's more for my benefit. It's a t-shirt. It's a little smaller than I expected it to be. And I don't know, look back at this later and be like, wow, that looks really terrible. So, anyway. If I find the decimal for that, let's look at the decimal for that. Let me pull up my calculator here. Okay, here's 20. And then the square root. 4.472135954999579, etc., etc., etc. Goes on forever, does not repeat. Okay? Negative 1.75. That is, again, it's a non-repeating decimal. It's terminating decimal, whatever you want to say. I'm writing words that I'm thinking and not actually what I'm thinking about what I'm writing. So, rational number. Okay? Terminates. You could also write it as a fraction, which is negative 1 3/4 is that fraction. And then negative square root of 121. Well, we have to say, okay, it's a square root, but the square root of 121. 121 is a perfect square. And so that is rational. Okay, so that equals negative 11, because it's negative out front, and we could write that as negative 11 over 1 or whatever. Okay, again, anything that is a perfect square, a square root of a perfect square, is going to be rational. Okay, your regular numbers, I can't see it because I can't tilt the camera, whatever, easily. Not messing anything up, but like the number line, any number you see on the number line, those are all rational numbers. Okay. Practice identifying them. Joseph wants to find the side length of a square that has an area of 150 feet. So the area is 150 feet. And so the side length of that would be the square root of that. Should that be rational or irrational, and why? Well, we look at 150 and we say, well, it's not a perfect square. 144 is a perfect square, and then 169. So it will be irrational because it's not a perfect square. It's the square root of a non-perfect square. I'm going to just write this. Square root of a non-perfect square. Which values from the following list is not a rational number? So 8.224, that stops. 5 over 9 is a fraction. We don't even need to find the decimal of it. That's some people are like, oh, let's find the decimal and find that it's 0.555555. You don't need to find the decimal if it's already written as a fraction. Okay? Square root of 25, that's just 5. So that's fine, that's rational. 0.321, that is 321, 321, 321, 321. So that's repeating, that's rational. Square root of 30, though, that one is not a perfect square. I hope I'm on camera this whole time, otherwise it's going to feel really weird. I'm not going to record it if I'm not, so whatever. I know that I'll be off if I'm over here, and that's fine. But if I'm like half on, that's awkward. So square root of 30, again, is the square root of a non-perfect square. This feels so weird to be teaching to nobody in the classroom, although it's about as much noise as my first periods of the day, so that's how it goes. Brad converted 5/11ths to a decimal, and his result was a repeating decimal. Does this mean that the value is rational or irrational? Okay, I don't really like that question. Why? Because it was already rational to begin with. So it's obviously rational. The fact that it's a repeating decimal, we need to not have this conversation, okay? It's a fraction, it's rational. So don't change it to a decimal. It's already a fraction. That's the big thing. Rational, ratio. Ratio, rational. Fractions are ratios. Okay, so if it's a fraction, it's rational. If it's a ratio of, I should say, two integers, which are numbers on the number line. Okay? When you have square roots and stuff like that in fractions, that makes some differences. Okay? But typical fractions that we are used to seeing, that's rational. Okay? State whether the given values are rational or irrational. So 3.4567. Now, if it went on and on and on like that, oh, like this one does, okay, this one here just stops. So that is rational, because it terminates. This one right here, 4, 5, 6, 7, again, probably 8, 9, I don't know what's after that, 10, 11, 12, 13, 14, I have no idea. Okay, that one is irrational because it does not end and it does not repeat, at least that we can see. And then 3.4567, and then that's a 7 with the repeating bar, 7, 7, 7, 7, 7, 7, 7, 7, forever, and that is repeating, which means it is rational. Okay, you want the decimal for that? I don't want to do it, so it's a pain. Or the fraction, I mean, it'd be 3 and something. Part of me is trying to figure it out really quickly in my head, but I don't. I'd be wrong, so I'm not going to do it. Okay, let's see. State whether the given values are rational or irrational. These are good ones. I like these ones. Okay, because we have to think. I know that 6 is rational. Square root of 30, though, is, as we did earlier, is irrational. It is a non-perfect square. So this right here is, in fact, let's just look and see what it is. Where's my calculator? Okay, 30 square root is 5.4772, all that stuff. Okay, if I add 6 to that, what's that going to change? Think about that for a second. What will that change? Will that change the decimal to a now it's not a crazy looking decimal? Or will it just change one part, the beginning? So instead of being 5 point a whole bunch of messy stuff, it is now 11 point a bunch of messy stuff. Okay? So that would be irrational. Oops. Pen. Okay? Now this one here, again, that was order of operation says to do that first, square root of 30, and then add 6. Order of operation says here, we need to do this thing inside first. So that actually equals the square root of 6 plus 30, which is 36. Now we can take the square root. This is where that whole, we had nuance with the please excuse my dear Aunt Sally, parentheses, exponents multiplied by add subtract stuff. Because this is grouped together underneath the radical. So we do the inside first, and then we take the exponent. So it actually, you can write this with an exponent, but we're not going to do that. So instead of the square root, and then you have parentheses and all that stuff. So anyway, so square root of 36 is 6, which makes that a rational number. And then here you have crazy stuff, 5 point whatever crazy stuff, and 6, square root of 6 would be what? 2 point a bunch of crazy stuff. So a bunch of crazy stuff plus another bunch of crazy stuff doesn't actually make something that's not crazy stuff. It is still going to be irrational. Okay? Yeah. All right, give it an example of an irrational number that is greater than 10. Irrational number greater than 10? I don't know. I know that 10 squared is 100. I know that 11 squared is 121. What if we just say the square root of like 150, which we saw earlier? Okay? That one gives us 12 point a bunch of crazy stuff. Okay? All right, so summarizing. I do want to summarize. Okay? Because this is important to recognize. Rational numbers always can be written as fractions. Sometimes we see them as a decimal that's repeating or repeating or terminating. You could say that, again, the terminating, we talked about this, the terminating decimals, you could say it is actually repeating, it's just repeating a bunch of zeros. Okay? In fact, if we looked at that on one of these earlier ones, we would see, we could just pretend like, oh, that's 0.00000. It's repeating as well. So rational numbers can always be written as fractions, though. And irrational numbers, okay, irrational numbers, from what we've learned so far, I mean, you can have the weird made-up ones, okay, and we see that, so it's non-ending, non-repeating. Okay, maybe we could include, I don't want to write it down, but you can write it down, terminating under rational, and write down also, or next to it over here somewhere, terminating or repeating. Whereas irrational is going to be non-terminating, non-ending, and non-repeating. So it goes on forever and it doesn't repeat. Typically, irrational numbers come from something involving pi or something involving a square root of a non-perfect square, or a cube root, or a fourth root, or fifth root, which we'll learn about another day. Okay. That was weird. So it's always one of those things for right now. There's other things, and they really do. The other things that you'll come across also kind of involve exponents and things like that. So they just look a little different, a little crazy. But irrational numbers, again, we recognize them by do they repeat or not? The other thing, perfect timing. Thank you, projector. Okay. The other thing that comes up when we look at this is when you're saying, I'm not sure, it looks like it might repeat, I'm not sure if it repeats or not. We talked about sometimes it could repeat after the calculator screen window or whatever. Again, so you have to look at where did my number come from? And that's the question I always, if people are not sure about whether it's rational or not, where did the number come from? Did I do a division problem? Did I do a square root? Okay, something like that. All right. Classifying real numbers. Okay, so we have this little example at the beginning. It says, over the summer, Ethan spent a week at camp. Ethan met several campers, including those from different states, to those that ended up being in some of Ethan's classes at school. The categories listed below describe the types of campers that Ethan met in no particular order. Use the graphic organizer, place the letter into each category where you think it belongs. Okay? So this is like if I'm in this group, I'm also in this group, I'm also in this group. So the most specific would be probably that they were in the same class at school. Okay, now if they're in his same class, that means they must also be in the same school, which most likely means they are in or from the same city. Well, if they're in the same city, that means they are from the same state. Now the other group that is out of state, they are not in any of those categories, and so they are all over here by themselves. And they are sad. But they'll be okay, because now they're friends with Ethan. And Ethan's a nice kid. He shares his Skittles. All right. I just had a kid when I was growing up, and he said he'd never had any Skittles, and if I didn't share with him, then he wouldn't be my friend. And so I shared with him, and then he moved away. He wasn't my friend anymore. And then I ran into him at scout camp one time when I was an adult leader, and he was an adult leader, and I didn't say anything about it. But I thought about it because it would have been really funny. All right. Ryan is one of Ethan's camp friends who is also in his first period class. List all of the sections of the graphic organizer that Ryan's name could belong. So if Ryan is in his first period class, he could be in there, right? So he could be in he's in the same class, which means he would be in the same school, in the same city, and in the same state. BDAC. BDAC. Okay? Which would be the best section to place Ryan's name in? Well, if he's in his class, that would be the best to be in B, because it's in all of the others as well. Okay? This kind of relates, if you think about in geometry with shapes, how like squares are rhombuses, which are rectangles, which are quadrilaterals, things like that. Okay, they fit certain categories, but it doesn't always come back the other way. Okay, just because someone's in his same city doesn't mean they're going to be in his same class or the same, etc., same whatever, same school, all that jazz. Okay, so now notice, and I haven't mentioned this yet, real numbers. He keeps talking about real numbers. Okay. There are numbers that are not real numbers. We call them imaginary numbers, or complex numbers is another name for them, and there might even be other things like that that are beyond what I can remember right now. Don't worry about them. You're not going to cover them for at least this year. I'm 99% sure you don't do it in 9th grade. I can't remember if it's in 10th or 11th, when it is. Anyway, don't worry about it. It's fine. It's fine. If you want to talk about it later, we can talk about it later. But it's not like 11D7 or something like that. It's different. Okay, so natural numbers. We don't talk about natural numbers a lot. because natural numbers is a set of all positive counting numbers. So numbers on the number line starting with 1. Okay? So it is 1, 2, 3, etc., etc., etc. 4, 5, 6, 7, 8. Up to forever. Whole numbers are the set of all positive counting numbers. So you notice it's the exact same thing, positive counting numbers, but starting with 0. Okay, so the natural numbers starts with 1 because you can't really find 0 in nature because you can't find it because it's not there. And so it's just weird. You count, these are sometimes called counting numbers. So whole numbers is 0 to forever. So this is why we don't really talk about natural numbers a lot, because we have whole numbers, and the only difference is that whole numbers now include 0, whereas natural numbers don't include 0. Okay, integers, this is very important, integers. We sometimes like, oh, what are integers? It's the set of whole numbers and their opposites. Hopefully I spell this right. This is always, the I does not look like an I, it looks like an L. So I'll take the L as a joke. Okay, so the set of whole numbers and their opposites. Okay, a lot of times that means negatives. That means negatives. A lot of times people see integers and they think that means negative numbers. It doesn't mean negative, it just means it can be negative as well as positive. Okay, whole numbers is all positive numbers, and 0, integers is all the whole numbers and their opposites. So all of the regular numbers. Negative, I'm going to put a dot, dot, dot here. -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. There's way more than 3 examples of each. We're overachieving. Okay, rational numbers are numbers that can be written as fractions. Terminating decimals, and this we talked about just barely. Terminating decimals, repeating decimals, and perfect squares. I really don't understand the need to include perfect squares in there, other than to differentiate between non-perfect squares. Okay, so this would be like 2/3, but also 2 is also rational, so it includes the whole numbers. And this is the kind of thing, is integers includes all of the whole numbers, and the whole numbers include all the natural numbers. So the rational numbers include the integers, -5, negative square root of 9, because the square root of 9 is 3, so that's a -3. Terminating decimals, 0.25 or 0.888, repeating. All of those are rational. And then irrational numbers are numbers that cannot be written as fractions. Okay? Non-terminating decimals, non-repeating decimals, and non-perfect squares. And we should say, I'm going to do this. Because it's not both, it's the same. Non-terminating, non-repeating decimals. Maybe I just need a comma. I don't need. We'll just get rid of that. Non-terminating, non-repeating decimals and non-perfect squares. Oops, if I haven't already written the letter. N-O-N, perfect. Okay. Non-repeating, non-terminating, non-repeating, and non-perfect. It's both. It has to be non-terminating, non-repeating. Did I say that already? I'm pretty sure I did, like 100 times. I probably should write square root of 50, 3 times pi. Let's make it negative. Doesn't matter. 0.10110111101110, etc., etc. It's just kind of a fun number to come up with. The pattern that is not repeating pattern. So anyway, place the headings for each of the type of real numbers in the graphic organizer below, then place each of the following into the box related along. So in the most specific, the box right here, this is where we find our natural numbers. Okay? When you do your test, it will not have the natural numbers, I don't think. It might. It usually gets skipped. I was surprised when we bought this curriculum stuff that we're teaching from that it had that in there. Anyway, so natural numbers, then we have whole numbers, then we have integers, and then we have rational. And then over here is irrational. Okay, and they're all real numbers. All of the numbers we're dealing with are real numbers. We are not doing any other time. So, 2 square roots of 64. Well, let's figure out what that equals. That square root of 64 is 8. 2 times 8 is, oh, that's 16. We did that problem actually in our notes, I'm pretty sure. I'm not sure why I just got some weird dots on it, but I did. Okay. 2 times 8 is 16, so that one, 2 roots of 60, that is a natural number. So 2 roots of 64. Negative 15. Wait, place each of the values into the box where they belong. So that one right there, 2 roots of 64, could also go there, and it could go there, and it could go there, and it could go there. So that means, again, it's in here. That means it's also in all of these other boxes that are in there. Okay, it's not in there, but it's in all these. It's negative 15, so there's no decimal or anything like that, but it is negative. That puts it into the integers. This is why we get confused sometimes with integers, because we only see negative numbers in there when we do stuff like this. Okay, but the whole numbers, like 16 over 4, is a natural number because that equals 4. Okay. So that's natural. It's also whole. It's also an integer, also rational. Square root of 75. That's the perfect square, is it? No, it is not. So it is irrational. It's between square root of 64 and square root of 81. So it's somewhere between 8 and 9. Okay. You want to figure out where, what's 11 away, and it's 6 away from the other one. It's, I don't know, it's somewhere. Probably 8.7 or 6 or something like that. Okay, 0. So, and this is weird, 0 is the only number that belongs in the whole number category and not the natural. So that's why we get rid of natural again. So 0 is whole, but again, all of these numbers right here are whole numbers. Okay? And so then the integer, same thing. This is integer. And then negative 12.2, that is a terminating decimal. But again, these are rational. Rational, rational, rational. All of those are rational, because they're in that box. For each set of values, list all of the number sets to which it belongs, and circle the most specific set of real numbers it belongs to. Okay, we're not going to list out the real number as one of the boxes, because they're all in the real numbers. Okay, I don't want to do that. We're not dealing with anything that are not real numbers right now. So 12 pi. Well, 12 pi, because it has pi and it's just 12 times bigger than pi, that's like Thanksgiving or something, right? It's irrational. Okay, just multiplying it by a number does not make it go away. Okay, there are ways I don't want to get in there. We're not getting there. Never mind. I'll pretend I'm going to remember to edit that later, and then I'll forget to edit it. So just pretend it got edited. So 12 pi is irrational. It's real. So it's most specifically. Anyway, I'm not going to do that. We're not going to circle all of them. Square root of 30 is also irrational. Okay, 45 over 5, that equals what, 9? I hope. Okay, so that one is natural. It is whole. It's an integer. And it's rational. And it's real, of course. So the most specific set is that it is a natural number. Okay? Negative out front. Don't forget that. Square root of 64, that makes it negative 8. That means it is an integer. And it is rational. Okay? 50.75. Okay, that is a decimal. It is a non-repeating decimal. It's terminating. So that makes it rational. 50 3/4. Okay? All right, an irrational number with a value greater than 10. We did that already in our previous notes. We did square root 150. You can do whatever. Integer between -5 and -6. Oh, that's tricky because -5 and -6 are right next to each other on the number line, and integers have to be a whole number type of thing, but negative or positive. In this case, it has to be, is there a number between -5 and -6? Not possible. Okay, sometimes I get my other hands drag a little bit. So it is not possible to fit a number between -5 and -6. Because their integers have to be, it's the opposite of whole numbers. There's not, only decimals are between there. Okay, I'm not going to write that. You can write that. A whole number less than 0. Well, whole number less than 0. Whole numbers are positive counting numbers starting at 0. So less than 0, not possible. For reasons just mentioned. Okay, whole numbers are positive and starting at 0. A rational number represented as a square root. So it's rational, represented as a square root. We could do the square root of 16. That equals 4. Okay? 4 is a rational number. You don't believe me? Write it as 4/1. We also did something the other day, though. We did the square root of 9/16, which was 3/4. And actually, we did one that we didn't realize we did, that I liked better. I realized some of you may not have seen this. But it was 0.81. And we could say 0.81 as 81 hundredths. And the square root of 81 is 9, and the square root of 100 is 10. And so it was 9/10. That was that 0.81, which became 0.9 as a square root. Okay? If we were going to summarize, what would you say? Let's say something like, I don't know. Just the key, I don't want to summarize this one. The key, though, is remembering all of those numbers. All of these numbers here belong in their other sets. Okay, so don't forget that. If I have a number and it is an integer, but it's also whole, it's also natural, it goes in the natural box. Okay, we're going for the most specific. Can I put it anywhere in the... So I would start at the middle box. Can I put it there? Yes or no? Now can I put it there? Yes or no? There? Yes or no? There? Yes or no? If I can put it in this one here, it's in all the rest of them as well. Okay? And irrational numbers don't belong in any of those boxes. They're just irrational. Comparing and ordering real numbers. Now we're looking at putting them from least to greatest, greatest to least, all that stuff. Okay, some of this is already filled out. We compare values by using the inequality signs. Not equal signs, but inequality, like the little arrow pointing left or the arrow pointing to the right. Okay? I think sometimes that the less than is a little, like almost like an L for less than, but it's also pointing left. And the greater than sign is pointing to the right. Right. So compare the following values by using inequality signs. We have 2 and we have the square root of 8. Well, I don't know what the square root of 8 is, but I do know that the square root of 4 is 2 and the square root of 9 is 3, so it's between 2 and 3, which means it's bigger than 2. So 2 is smaller. Negative 1.5, negative 5 over 2. That would be negative, what's 5 divided by 2? 2.5, right? So which of those is bigger or smaller, whatever way you want to think of it? Actually, that one is bigger, right? Because it is further to the right. Okay? If I owe someone $1.50 versus someone owes someone $2.50, I technically have more money or less negative, whatever you want to say. Okay? I'm better off. 12.5 and then the square root of 145. I don't know exactly what that is, but I know that the square root of 144 is 12, and so I'm 99, moving to 100% sure that this 12.5 is going to be bigger than that. Okay, because the next perfect square is 169, and 145 is not anywhere near halfway between 144 and 169. Okay. So sometimes we order them from least to greatest or greatest to least. We also sometimes, instead of those things, we say like ascending order or increasing order, minimum to maximum. We don't really see that a lot, whatever, but it's okay. We see descending order, decreasing order, maximum to minimum, stuff like that. All right, when comparing or ordering, it's helpful to first represent the values in the same form. Okay, this is where I talked the other day about repeating decimals in the little repeating bar. Why I don't always like them with the repeating bar, because it's technically not, I don't want to say technically, it doesn't seem like the same form to me as the other decimals. So the fraction for 1/3 and then the decimal for 1/3 is 0.333, okay, and I can just write 0.333 is fine, but I like to keep that. As a percent, we just move the decimal 2 places, 33.3%. Okay, 0.2, move the decimal 2 places. We're trying to find what it was out of 100. So 0.2 out of 1 is 20 out of 100. It's 2/10, which is 2 over 10, and then you just add an extra 0 on all of them, so it's 20 out of 100. Which is writing that as a percent, because I didn't do that, apparently is 20%. As a fraction, there we go. 20 out of 100, which should have been 2/10, which should have been then 1/5 is what it reduces to. 50%, that is 0.5 as a decimal, and 1/2 as a fraction. Okay, or 5, it goes from 5/10 and then to 1/2. That's why there's no 5 there. That's kind of weird. 2/3 as a decimal is 0.6666, or 0.667 if you want to round. Percent, 66.67%. 0.75 would be 75%. That is 3/4. These are just some common fractions that over time you should kind of learn what the fractions and what their decimal values are if you don't know them already. Some of you know some of them. All of these are ones that, like the 1/5, 2/5, 3/5, 4/5, okay, all that stuff. 12.5. Dividing, since that's 12.5 out of 100, we move the decimal the other way, and we have 0.125 as a fraction. How to make that into a fraction? Well, I could do 125 over 1,000 and then divide each by 25, and that would give me 5 over 40. Then that can actually reduce by 5 even to become 1 over 8. Okay. There's also a trick. Let me grab a calculator. I'm using this calculator. We're going to see if I can get it up close enough to where it's viewable. Okay, I'm turning it on. And there's already a number in there. So if I do 0.125, here's this cool trick. I'm trying to see if I can see it on the screen very well. So then I'm just going to hit enter. I probably don't need to do that, but then right here, it's different places on different calculators. Right up here, there's a little, you can see that F, arrow, arrow, D. So I hit the second function because it's above it, and so I have to hit that, and I do that, and it shows up on my screen. It's just saying the answer was whatever the last answer was. F arrow arrow D, that goes from fractions to decimals and back and forth. I hit enter, and I get 1/8. Okay, cool. This is going long, 45 minutes already. Almost done though. So 2/5 as a decimal, 2 divided by 5, that's going to give us 0.4, and that's going to be 40%. 1.5, move it 2 places, is a 150%. And I can put 1 and 1/2, or I can put 3/2. Either way, both work. Okay? Compare these following. We're on the first side still. Okay, almost done. So close. Look at that, getting right there, and then we'll be done. Whew. I hope you can watch this at like a faster speed, because I know that sometimes I talk slow or I ramble. So -7/8 and then -0.5. Well, there's a lot of it. I can convert that to a decimal if I want. I could also just say this is -1/2, which would be -4/8, and then it makes it easier to compare. So -7/8, -4/8, well, -7/8 is going to be less than that. Even though 7/8 is bigger than 4/8, remember, because it's negative, it's the opposite of that. Okay, and I can't, my number line's up there. Think about a number line, visualize, oh yeah, it's further, 7 is further away than 4. Okay, pi squared and the square root of 50. Well, we would need to find out what that is. I wonder if I have a pi button on my calculator here. I don't, because it's not in scientific mode. And I think if I go to scientific mode, it might not be very legible. It's hard to read. Where's pi? There's pi. And squared. 9.869. 9.869? Well, that's, oh, duh. Okay. Well, obviously that was 3.14. 3 times 3 is 9 point something. And then square root of 50 is going to be 7 point something. That's a question mark. I don't know. Whatever it is. Let's just do that. Let's do 7 point whatever. 9 point whatever. And obviously the 9 is bigger. -60%, -3/4. Again, so this is -75%. It's 0.75, so -75%. And 60% is bigger in the negative than 75. Again, it's opposite. It would be nice if there was just some regular positive numbers here, like, oh, whatever. Okay, this one's tricky, but square root of 60 is going to be 7 point something. Square root of 63 is also going to be 7 point something. It's a little bigger than that one, right? This one's closer to 8 than this one is. Okay, but this is 4 plus 7 point something, so that's 11 point something. And 5 plus 7 is 12 point something. So without even having to find the actual values, we can find that this one is bigger because we did find that that's bigger by finding that it's bigger. It took Kiara 35.25 minutes to finish her chores. It took her brother Derek 35 1/6 minutes to finish his chores. Who finished their chores the fastest? So they both took 35 minutes. I'm just happy they did their chores, really. I mean, come on. So that's 35 1/4. That's 35 1/6. Still doesn't help. I'd have to get a common denominator. I can do that if I want. I might, though, just say 35 1/6, and I go doop, beep, boop, beep, boop, beep, boop. 1 divided by 6 is 0.16. So that's 35.1667, whatever. It would be 66666 repeating, but we're just going to call it that. And I really don't even need to write it out that far. And I'm rambling. And who finished their chores the fastest? So Derek did. Derek probably had the easy chore, like clearing the table, which is kind of not fair sometimes. All right, descending order. This is tricky. So this is going to be, that's 11. That's 9 point something. That's 11.1. And then square root of 130 is going to be bigger, and we can figure out what it is using a calculator. We could estimate like we did before, but I'm just going to write square root of 130 in my other calculator and find that it's 11.40175,425. We're just going to leave it at 11.4. Okay? Descending order. So that means descending order is the biggest to the smallest. So square root 130 and then 11.1 and square root 121 and pi squared. Okay? I want you to try the rest on your own. Okay? Try those rest of those on your own. Pause it for a second and then I'll go over it. So just pause it. I'll wait. Go ahead and pause it. Do it. If you haven't paused it, you should have paused it already. Okay. Did you unpause it now? I didn't tell you to unpause it, but you should. Unpause it when you're ready. Okay, so 0.65, 6.5%. Saying we want to maybe them all decimals. That's 0.65. It seems the easiest to compare. So that would be what, 0.065? Because it's a, wow, nice writing. Lost control there. 0.065. And 2/3 is 0.6666666. Add an extra 6 there. And then 1/2 is 0.5. So write the list in increasing order. You got to pay attention to that. Hopefully you paid attention to that as you're going. If you didn't, it just reverses things sometimes if you didn't pay attention. So increasing order means the smallest one first. That would be 6.5%. And then 1/2. And then 0.65. And 2/3. And there might be a better way. If you want to do it a different way, you can. You can find common denominators and stuff, or however you want to do it. Least to greatest. Least to greatest of smallest to biggest, that's -5. This is -5.1, so 1/5 is 2. And then 11/2 is -5.5. So least to greatest means the furthest that way to the left, which would be this one, -11/2. And then the next one would be -5.2, which is -5 1/5. -5.025 and negative square root 25. Okay, that's least to greatest, which is the opposite because they're all negative, which can be tricky and backwards and annoying. 43%. Ascending order. Ascending means we're going up to the right, left to right, biggest, smallest to biggest. Ascending. Okay? So 0.43 and 2/5 is 0.4. 3/7. That's not a very common fraction. It's 0.42, but we'll show you that just so you can see it. If I can actually get, waste time doing that. All right, so it was what, 3/7? 3 divided by 7 equals 0.42857. So let's say 0.43. Oh, shoot, we can't. Let's do 0.4287. 4285. 4286. Oh, son of a gun. Wrong thing. 0.4286. We're going to round it. Okay. And then 0.42 repeating. So that's 0.4. This is why I like not the repeating bar, because I like that. Okay, so least to greatest, that makes this a little bit nicer. So the smallest one, and I think about that, would be like zeros, so that would be 2/5. Okay, 0.42222 and 3/7 and 43%. Alright, decreasing order, that means going from biggest to smallest. Okay, so that would be 5.5 square root of 26. Pull out the calculator just to get a good accurate answer. If you're doing the calculator, you gotta usually look. It doesn't always have a square button or whatever, and so a lot of times it's right here above the square. There's a little square root. So I have to hit second function, and then the square root. Some of them have their own square root button, and then I hit 26. And I don't have to close the parentheses, but I could, and it's 0.509951. So 0.5099. Or 5.099. That's what I meant. 5.099. Okay, 5.8. It's 5.8. And then 31/5 would be 6.2. I was pretty sure, but I wanted to not mess it up. Decreasing, so biggest to greatest, biggest to smallest. I don't know why this is like registering weird things. So we got 31/5 is the biggest. Next biggest is what, 5.8? And then 5.5, and then square root of 26. And greatest to least, we're almost there. I want to get done. 28 divided by 3 is 9.333. Negative 9.333. Repeating. Negative square root of 64, which is 8. Negative 7.9. Negative 8. And then 6/7. I'm pretty sure is... Actually, I'm not at all sure what it is. I'm pretty sure it's like 0.86. Let's see. 0.857. 0.857. 1/7 is 0.14. So that's where I was kind of going off of there. 1428. 142. Yeah. Anyway. So greatest to least, which is the biggest one? That one. Negative 28/3. Would be awesome if it was already written that way, right? Negative 8 6/7. Negative square root of 64. And negative 7.9. All right. And lastly, 12. Today's low temperature for 4 different towns is shown below. List the towns in ascending order according to their temperatures. They live in the wonderful village of Chillyville, where they decided to express their temperature as a square root of 48. I would consider moving from any one of these places, except maybe Shiverton. Okay, so negative square root of 48. Square root of 48 is 6.9, so negative 6.93. Ascending order. Negative 6, that one's obviously like negative 8 point something. 7.5. And then 22 divided by 3 is going to be 7.33 if I remember right. I guess we didn't need to find the actual number there. So we have what, again, it's from ascending order. List the towns in ascending order. So, from, that would be going up, right? Getting hotter. So the coldest one is Icetown. Icetown, baby. Do. Icetown, baby. Then Shiverton. Riverton? More like Shiverton. It's a great weather joke. I'll tell Mark Eubank. And then what one? Then Little Flake. And lastly, Chillyville. All right. That's it. Okay, you made it that far. As your reward, I don't know if I was going to think I was going to do floss, but I can't remember if I can even do it anymore. Yeah, kind of, a little bit. I'd have to like really get in the groove of it. I'm a little nervous to go really fast with it. So, anyway, that's it. Go Utes. Peace. Carol Baskin, kill her husband.